Okay, you can start.
Okay, so good evening, everyone. I'm going to speak mostly English because, believe it or not, I cannot explain any of this in Russian to save my life. But today, my name is Karyna. My last name is Pryiomka, and we're going to talk about quantitative reasoning with descriptive statistics. Just a few words about me. I'm a doctoral candidate in social personality psychology program at the Graduate Center at the City University of New York, and I work as a lecturer in the psychology department at Lehman College within the City University of New York. I teach primarily statistical methods for behavioral sciences, primarily psychology, but with some application to sociology, a little bit of marketing, but mostly psych and experimental psychology. So that's kind of like, research methods is the area where I live most of my kind of academic life. And today, what we're going to talk about is kind of a very simplified and condensed version of descriptive statistics, of overview of descriptive statistics that usually kind of covers about the first third or fourth of an undergraduate stats course. So some of you might find it as a welcome review of some of these concepts. Some of you might find it as a good refresher or an introduction to some of the concepts that are important to think about as we analyze data. So just a kind of quick overview, there are two categories of statistics when we talk about more broadly. The descriptive statistics, which are usually the first steps of analyses, the tools and procedures to summarize, organize, and simplify data. So we're going to talk about some of these today. And then there are inferential statistics, which some of you might also already be familiar with, tools and procedures used to study samples to make generalizations about populations. So these are your hypothesis tests, your t-tests, regression analyses, your p-values, and so on and so forth. So usually like a second layer of analysis that is typically more complex, and you can take the entire specialization in just one of those methods. So we'll keep things simple today. Feel free to interrupt me, ask questions, tell me to go faster or slower, right? Again, you're here, so you drive the show, and those who will be watching later can also skip or slow down, of course, as they see fit. So the types of descriptive statistics that are kind of typically covered and used to explore data at the earliest stages of analysis are frequency distributions, which can take the shape of tables or graphs and graphs. Measures of central tendency, very familiar, mean, median, mode. And measures of variability, range, variance, standard deviation. Today, we're going to primarily focus on these two and how they work together and how to think about them together when you analyze data or consume data that have been, analyses that have already been prepared and presented to you by other people. And at the end, I will say a few things about measures of variability, but I'm not going to go into detail because I typically find that topic a little more complicated, so we won't have time to dive into it with more depth that I would have liked. So a frequency distribution, usually one of the first steps in the exploration of data. You typically want to create one for every variable in your data set just to kind of see what's inside of it, what's inside each variable. So what is it? It's an organized tabulation showing the number of individuals or objects located in each category on the scale of measurement. In a very simplified terms, it is just a summary of how many people or objects fall into each category of the variable that you are measuring. So you want to see how many people or how many objects are within each particular category that exists within your variable. And the frequency distributions can take a form of a graph or a table, and you can commonly see both presented depending what kind of sources you are consuming. And of course, depending what kind of data you're dealing with, sometimes graph is more preferred than the table. So here is a very simple example, right? So let's say we have a question: how many siblings does someone have? And a frequency distribution table will typically look something like this. The first column will outline the categories within the variable. So as people were answering the question, some of them said 0, some of them said 5, some of them said 8 or 9. The second column here will specify the actual frequency, right? How many people provided a particular answer, or how many objects fell into a particular category. The third column will typically be the proportion of that category of the total, and the last column will be the percentage. When you prepare technical reports, you might present the entire table. It is very common to just focus on proportions or percentages when reports are prepared or presented to a larger audience. And the reason for that is that raw frequencies are typically very uninformative, right? So if I tell you that, 2 people have 5 siblings, that doesn't actually tell you much about what that number means or how significant it is. But if I tell you that about 12% of my population sample, whatever, have 5 siblings, that number is a little more meaningful. This is why presenting proportions or percentages is typically more common rather than presenting raw frequencies. When I prepare reports, I typically present both because I want my audience to have an ability to recalculate and group categories as they see fit. So I see it as just kind of responsible data presentation, so the audience has more autonomy and transparency in terms of how to consume and interpret my data. The graph for this, in this case, would be what is called a histogram. And right, so that's the representation of the same data that you see in the table, but in a kind of a more, sometimes easier, more easily consumable way, sometimes not, again, depending what kind of data we are looking at. So the height of each bar represents the frequency, can represent the percentage, again, depending how things are being graphed and presented, for each of the categories being presented on the x-axis, right? So the y-axis is the frequency, and the x-axis are the categories themselves. Typically, right, you can see, sometimes we see smooth curves kind of over the graph. They're not always presented as bars. They're sometimes presented as smooth curves. And again, the height of the curve, right, at a particular point typically represents the frequency of the category that is kind of corresponding on the x-axis. So that's kind of the tabular or graphic representation of a frequency distribution. Again, very common, right, in technical reports, very common in academic presentations, and are a very, very important tool for initial exploration of the data. Again, whenever you see a new data set, this is one of the first things you want to do, just kind of create a frequency distribution for every single variable, just to see what's inside, like what's going on. Distributions have different shapes. So not all of them are created equal. Sometimes they can be pretty funky. They can, look very weird, but there are kind of some typical shapes that we see, particularly in social sciences and some other kind of disciplines or professions. The most common, and you're probably all familiar with it, is the normal distribution, also known as the bell curve. And this distribution falls into the category of symmetrical distributions. And by symmetrical distribution, I mean, if I draw a line right through the middle, the left side will equal the right side, right? So the line will divide the distribution in exactly 2 equal halves, right? So it's symmetrical around the center. Again, we're talking about frequency distributions, right? So we always want to imagine this kind of y-axis that tells us the frequency, and the x-axis is whatever variable we are representing. And so the middlemost point is also the most frequent category, in a normal bell curve distribution. But not all symmetrical distributions are normal or bell curved. So we can have a distribution like this with 2 frequent points, which is called bimodal distribution. We'll come back to it in a few minutes. But again, the idea is that if I draw this line in the middle, the left side will be equivalent to the right side of the distribution. So again, there is symmetry around the center. The other 2 common types of distributions that we see are skewed distributions. And we can have a positive skew or a negative skew. The shortcut that I typically tell my students how to distinguish the 2 or remember is you always want to follow the tail. So if you look at the number line on the x-axis, you know that numbers go from negative to positive, left to right. So if the tail of the distribution is pointing to the positive direction, it is a positively skewed distribution. If the tail of the distribution is pointing to the negative direction, it is a negatively skewed distribution. So you always follow the tail. Whenever you're confused, just look where the tail is pointing. If it's in a positive direction, it's a positive skew. If it's in a negative direction, it's a negative skew. These distributions are a little tricky, and we'll look in a few minutes at why. But again, the highest point is the most frequent category, right? The kind of most common category within the distribution. And then the tail kind of tapers off, right? So the tail represents, again, the least frequent categories. And so the distribution itself is kind of lopsided. So you have more values on positive or negative side and fewer values on the opposite side. And the middle is actually not as clearly defined as it is in like a bell curve distribution. So here are a few examples of these. So the most common positively skewed distribution example is usually income, right? So the income distributions tend to be across the board kind of more positively skewed, with kind of a large number of people actually making kind of less amount of money and a few people existing in the tail making kind of increasingly more money, but there are fewer and fewer people who make more and more money. So this is the distribution of household income for 2014 from the Census Bureau. Unfortunately, I wasn't able to find the actual histogram like this for a more recent data, but the good thing is that the median income did actually increase from 2014 to now. So that's, I guess, good news, but I don't have an equivalent updated distribution for you at this time. So real estate prices are another example of a positively skewed distribution. You have a few properties at a very, very high end range, and then you have kind of a large number of properties in about kind of a lower or middle range. Negatively skewed distributions, I typically would say are less common, again, depending what field you're in. But here is a good example, and that's the age at the time of death. I'm sorry of being morbid on this Friday evening, but right, that's an example that I was able to find. So more and more people live till longer age, right? They live into their late 70s and 80s. Very few people, thankfully, die when they're young. And so we have a negatively skewed distribution when we look at age at time of death. And again, here we see a comparison from 1950s to 2015, which looks pretty good for all of us. So these are distribution shapes. We'll come back to them in a few minutes, but before we do, I would like to kind of proceed to measures of central tendency as our second kind of big topic. So measures of central tendency are kind of the goal for their creation and existence is that to summarize the entire distribution with just one number. You encounter them very, very frequently on the news. They create very good bullet point and sound bites, right? The average income is this, the median household, right, or a real estate price is this, right? The family has the average number of children is this, right? So it's kind of like one number that is designed to summarize the entire distribution and kind of simplify our ability to work with data. So there are three of them. The first one is the mean, or arithmetic average. We're all familiar with it, depending whether we use it or not, right? So it's the sum of all the scores divided by the number of scores in the data. So here in my imaginary example data set, I just add all the scores together. There are 19 total. So my average is 3.05. The median is the midpoint of the scores in a distribution when they're listed in order from smallest to largest. So that's your kind of 50th percentile. That's your hard middle, right? So you kind of use, when you slice your distribution at the median, exactly 50% falls below that number and exactly 50% falls above that number. And we'll talk in a few minutes why it's actually often a much better representation of the data than the average. And then we have the mode, which is the score or category that has the greatest frequency of any score in the distribution. So in this case, right, if we look at my data, we have 3 1s. We also have 3 2s. We have 4 3s. Then we have 8 4s. And only 1 5. And so the most frequent value in my data set is 4. It occurs 8 times. And so that's the mode. I'm going to stop here for a second, see if anyone has any questions before we proceed. And if I speak too fast, please tell me to slow down. I sometimes get a little nervous. All right. So the key, right, or one of the critical questions that we want to ask ourselves when we work with data and when we present, right, when we're analyzing data or preparing presentations for other people is which measure of central tendency to use. Again, right, they're kind of designed to summarize the entire data set, right, usually the entire variable. And so how do we decide which one is a better measure? Or when we consume data, right, when we work with information and somebody presents us with data, we want to kind of think through critically, like, is something missing? Are the numbers they're presenting to us can be potentially misleading? What kind of questions can we ask them in order to clarify and see whether the information that is presented is being interpreted accurately? So the first step or the first question we want to ask ourselves is, what scale of measurement are we using? Or kind of in more simple terms, what does our variable represent, right? And kind of what makes sense in terms of analyzing that variable. So there are nominal variables, right? The variables that are measured in name-based categories only, like eye color, academic major. They're not ranked, right? Race, ethnicity, they're not kind of numerically related in any way. These are just categories. And for these variables, mode is the only option. The only thing you can say is, right, this is the most common eye color, right? Or this is the most kind of purchased product, right, in our inventory or something like that, right? So the, kind of the most frequent value is oftentimes your only option. And with these variables is the only option. The second type of variables are ordinal variables that represent ranked categories, not necessarily numeric, right? So like a shirt size would be small, medium, or large. We can rank them. The categories are numerically related among each other, but they're not necessarily numeric in the sense that, right, they're represented in numbers. Likert scales are typically considered ordinal variables, and Likert scales are those very common survey items that you see, like on a scale from 1 to 5, how did you like your experience, right? They're measured in numbers, but depending who you ask, they're typically considered ordinal variables rather than interval or ratio variables, which are the third category. And again, the kind of most kind of common or even necessary for a lot of the inferential statistics, right? So these are numerical variables: temperature, height, weight, income in dollars, things that we can typically count and quantify reliably. And for these variables, mean and median are preferred. For ordinal variables, mode and median are preferred. And again, for nominal variables, mode will be your only option because there is no way to calculate anything or rank them in any way to find the middlemost value. So you want to think about, okay, what my variable represents, how it is being measured, what the categories are, what makes sense, right? Can I actually add things up, right? And kind of find the average, or is this impossible, or doesn't make any sense? So there is a great episode of Planet Money podcast called The Modal American, which I absolutely recommend. I require all of my students to, we have like an assignment that we do related to it. And this is one of those kind of it's a 30-minute discussion of how we often misspeak or misrepresent the information when we say average American. And as one of the guests on the podcast kind of pedantically points out, is that when we say average American or average person, we don't actually mean average, we mean modal. We mean the person with the combination of characteristics that are most common in the population, or as they say, who is the person I'm most likely to run into when I go outside. So mode is typically the most useful statistic when you're trying to identify a typical person, typical customer, client, student, right, whatnot. Because again, when we say typical, we mean a combination of categories, right? Of course, if the only thing you're concerned with is just age, then it doesn't matter. You will take probably the average or the median. But if you want to see a combination of categories like, place of residence, rural versus urban, education, higher education degree versus no degree, right? Gender, ethnicity, income level, right? And you want to combine those, you are actually looking at the mode. You're not looking at the average because most of those categories are not even quantifiable. So that's just kind of a little thing to think about. Another thing to think about when we're considering mode and variables that we are working with is what we call discrete variables. I don't have a separate slide for this, but this is important to mention. There are variables where we can count things, like for instance, how many siblings you have or how many children does a family have. However, when we calculate the average, we often end up with a fraction, right? So these variables are called, we call discrete variables that are not continuous, they don't exist in fractions in the real world. So when somebody tells you that an average household or an average family has 2.5 children, this is kind of meaningless because you can't have half a child, right? So you do want to use the mode or the median to represent discrete variables, because again, the fractional value is I want to say misleading, but it's kind of nonsensical when we're talking about discrete variables, because again, people like siblings or children do not exist in fractions. And so we want to represent them in whole numbers. And so the mode or the median are typically a much better representation. Although again, very often still encounter in various reports, the average number of, students, children, siblings that are represented with fractions, which again, is not usually looks a little weird. The second thing to consider when you're deciding how to represent the data, or you're looking for things that might not look right or feel right, is the shape of the distribution, right? So this is where we are coming back to this idea of symmetrical and skewed distributions. So in a perfect normal bell curve, the mean, median, and mode will be in the same place. So if you have a bell curve, it doesn't matter technically which number you pick. You want to look at the variable measurements. You want to see what makes sense, but those numbers will pretty clearly be aligned with each other. Not perfectly, right? No real world data is perfect like it is in textbooks, but it's pretty close. In a bimodal distribution, right? So the distribution that has more than one high frequency value, if it is symmetrical, the mean and the median will fall right in the middle, but there will be two modes. So again, you want to ask yourself what makes sense, right? Does the mean and the median, because they're the same, are a good representation of the data? Or should I kind of, present the graph or make a note, for my readers or audience that the graph actually has multiple modes? And a uniform distribution, which is the distribution where every category has the same frequency, typically, right, has no mode because every category has the same or very close to the same frequency, and the mean and the median still fall in the middle of the distribution. Median by definition, because it's the middle of the distribution by its very kind of definition, and the mean because of how it's calculated. So because the distribution is symmetrical, the numbers balance each other out on each side. So let me show you a few examples where kind of why I always say, look at the graph. Don't just trust that one number. So I don't know how many of you have watched or even familiar with the show The Romanovs. It's just Amazon original, kind of, in a very kind of simplified explanation. It is a show about supposed descendants of the Romanovs family who are kind of trying to find their relationship to the family and claim their royal ancestry. And so it was one of those Friday nights when I was trying to decide what to watch, and I looked at the review, and the review looks pretty good. It's kind of like an average show. You don't have to think really hard, but you might find that you're enjoying it. And so if you have one of those nights where you don't want to think about or dig deep into convoluted plot, this might be something to spend your time on. And so I watched it. And as I watched a few episodes, I was kind of like, this is a very weird show. This is not your average show. This cannot be just like an average experience. And it wasn't. It turns out that people tend to either love or hate the show. And if you ever watched it, you probably felt the same, because that's exactly the vibe that I was getting. Like, you're either like really, really into it, or you think, what the hell are these people trying to say here? And so the average review is 3.3, but only 5% of reviewers actually gave it a score of 3, right? Nobody felt like it was your middle of the road kind of show. Most people either really, really liked it or really, really disliked it. And so that's one of those examples where when you look right at that one value, average or the median, and in this case, those will be very close because this is the binomial distribution, you are missing a very important piece of a puzzle, that not every customer has the same experience. And so whether you are analyzing customer data, let's say you're working for a business and you're tasked with like figuring out what the customer experience is, or you're making your own choices with products, you always want to, again, kind of see what the underlying distribution looks like, because those average numbers can often hide very important pieces of information. I have another very similar example, a little more recent and kind of relevant, I guess. I'm not affiliated, again, with any of these products. These are just interesting examples I find and put in my lectures that I think illustrate these points very clearly. So again, right, a very, very distinct bimodal experience with the product, right? 5-star reviews or 1-star reviews, but they balance each other out. So when you calculate the average, you get that 3-star review and you might think, well, hey, this is, not so bad. But in fact, right, if you fall into the 5-star category, that's excellent. But if you fall into a 1-star category, which are, again, those two most likely categories of experience that you're going to have with this product, right, you are kind of in for a great experience or not so great experience. A 3-star experience is very, very unlikely in this case. So again, bimodal distributions can present a little challenge. And again, you want to look at the graph to figure out what kind of shape you're dealing with, because even if your mean and median line up, this does not necessarily mean that you're getting that bell curve, right? Or you're getting the kind of a normal distribution. You want to be aware of potential bimodalities in the data. The skewed distributions are also a little tricky because that's where the mean, median, and mode fall into different places. The mode, again, will always be at the highest value, right? That's your most frequent category. The median will always be in the middle because that's the value that divides the distribution in half. And the mean will always follow the tail. So the mean will always follow, right? It will be the highest value of the 3 if it is a positively skewed distribution because you have a lot of high values at the tail, or it will be the lowest value because you have a lot of low values at the tail in a negatively skewed distribution. So let me show you where that matters and kind of how this looks like in real world data. So these are salary examples. These are, I believe, 2020 salary distributions from the Bureau of Labor Statistics. These are for psychologists, but I also have others to show. So if you look here, what I respect about this data presentation is that we see both the median and the mean hourly wage. And you can see that the mean in pretty much every category, right, for psychologists in general, but also clinical psychologists and industrial organizational psychologists, the mean is always higher than the median, which suggests to us that there are some skew in the distribution with potentially fewer people making more money and more people making less money. And that particular kind of deduction actually plays out in the data. So this is a slightly older data from the American Psychological Association, but we do see that the distribution of income is in fact positively skewed with a few star psychologists, right? Those who have business contracts, right? Department of Defense contracts, if you're talking about military psychology, right? Who can be making a lot of money at high-end universities, but the median income is $85,000, right? So if you're considering a career change, right, or know someone who wants to go into psychology, right, you're probably looking at 50% of everyone in the profession making $85,000 and below, and then another 50% making more than that, with higher salaries being pretty uncommon, right, and not as frequently distributed. And again, we can see that in that mean and median relationship here in the data. Similarly, we can see that in, let's say, legal professions. So lawyers, very commonly discussed profession, very commonly chosen profession among Russian immigrant families and other immigrant families. And I have a few friends who are lawyers. And so when you look at the distribution of income here, again, you will see most of the time that the mean income is pretty significantly higher, right? By $14 sometimes, or $10 higher than the median income, hourly wage, sorry. The interesting thing is when we look at these categories where we see them broken down a little more in a more nuance and detail, we have a $10 discrepancy for lawyers. We have about $3 discrepancy for judicial law clerks, and almost no discrepancy for judges. Because again, right, if we think about logically, right, what the distributions might tell us, lawyers can work in the corporate, private sector, some make a lot of money, some work in the public defense office, make not so much money. Judicial clerks, depending what ranking they in, might make a few bucks here or there, but judges, right, are public servants. So their income distribution should be pretty fixed. There should not be just one judge that makes millions and millions of dollars and another judge that makes $20,000 a year. So again, we want to see both numbers if we are unable to see the distribution, so that we can at least reason through what the distribution might look like, right? You don't want someone telling you average hourly wage for a lawyer is $71, because that might not mean much, right? You might not kind of get the accurate picture of what lawyers are actually making from that number, particularly knowing that there is a huge range there. And the interesting thing is that, again, depending how you break your data or what period of time you look at, here is another example, still with lawyers, where the distribution is not technically bimodal because there is a higher peak at a higher salary range compared to the peak at a lower salary range. But in this particular example, these are the starting salaries, right? Full-time salaries for the class of 2020. So very kind of relevant recent graduates. So according to this, 50% of the respondents make between $45,000 and $75,000, and 21% make $190,000 or more. The average is about $100,000. So actually, the average, again, is not representing the most likely salary that a law student, right, finding their first job, right, a full-time job, will be making, because of those two peaks, because of those two kind of heavy clusters, right, at each end of the distribution. The mean becomes very uninformative and may potentially be misleading, and depending on what kind of decisions you're trying to make, might even be harmful, right? Again, depending what you are working with or what kind of decision you're trying to make. So always, right, I always say you want to see the distribution, right? You want to graph the data, because as simple as it might sound, that one number, the median or the mean, is not always the best kind of clear representation of the data at hand. But because of the skewness in a lot of the variables that we typically work with or think about in our daily life, like salary, cost of living, and things like that, when you consume media sources, you know that you're most likely to encounter medians than means when people are describing income or real estate prices or many other variables. And I often encourage students and others to kind of question when the averages are presented, because when the average is presented, you do want to see some kind of explanation whether like that the average presentation was warranted, right? That the data was fairly normally distributed, right? Or it makes sense. There were no like severe outliers or things like that. Then the mean wasn't the best option, because the mean at least has a very clear definition of what that means. You know that 50% of people are below, 50% of people are above. It's a very clear number, at least from that perspective. So we looked at how the data are measured. We looked at relationship between central tendency and the distribution shape. And the third thing to consider are the data themselves, like the kind of little bits and pieces of the data inside your data set. Are there extreme values or outliers, right? Is there a data point that is so outrageously different from all the other data points that it is skewing your data or it's muddying up the results? You always want to find these data points, and you always want to ask yourself, okay, is this just some kind of weird case? Is this a data recording error, right? Does something go wrong, whether the data was recorded automatically or somebody had to type in the answer, right? Did they type in the wrong thing, right? You always want to kind of question the origin and the meaning of the outliers in your data. And there are a whole host of books and articles on how to deal with outliers. Some people say you should exclude them from the data. Some people say you shouldn't. The most common kind of advice that I see is that you want to run the data, including the outlier and excluding the outlier, and see how much effect the outlier has on the outcome. And usually you want to present both. Undetermined values, right? How many hours a week you're studying? 4 to 5, 6 to 7, about 15, right? Again, there is no clear number, right? So the value is not determined. You get some kind of range or you get some kind of approximation, but you can't do much with these data, right? You can't calculate a reliable average. Oftentimes, you might not be able to even find a reliable median, depending on how the data are being recorded. This is where, again, right, you want to think, right, if you're only working with the data and have no say in how the data are being produced or recorded, it might be kind of very tricky because sometimes you might not be able to do much with the variable if it is being recorded in this kind of very kind of strange or unhelpful way. And open-ended distributions. So open-ended distributions, things like, again, like let's say how many children does someone have, right? 1, 2, 3, 4 or more, right? So this is an open-ended distribution, can be 4, can be 5, can be 6, right? So these 4 people can have whatever number of children that is 4 or greater. In this case, average is impossible to calculate because to calculate the average, you have to know every single number in the distribution, but you can still find the median. You can still oftentimes find the median depending how many open-ended values you have. So again, you always want to look at what's in your data, kind of like what's inside to make the determination which central tendency is even possible. And also the most appropriate. So here I have a very neat summary table from the textbook that I typically use in my courses that kind of outlines which measure of central tendency is appropriate in which cases, and in which cases it can be misleading, right? And potentially kind of misrepresent the information that you're trying to convey. Or on the other hand, right, when you're a consumer of the information, you want to use this knowledge to kind of ask critical questions, right? If somebody tells you the average XYZ, you want to say, okay, right, do I just trust them that they considered extreme scores? Do I just trust them that they considered, right, all these things? Or is there an explanation, a methodological note, right, if it's a technical report? So you want to be vigilant and critical in how you evaluate the data that is presented to you, as well as how do you calculate and present the data to others. So that's selection of measures of central tendency in relation to the distribution shape. So this brings me to kind of the final few notes that I'm going to say today. Like I said, we're not going to have time to dive into much into the distribution variability, but I did want to say a few things about data variability that I find important, and I feel like that discussion warrants a whole separate meeting. So here is a very simple example, right? You can think of it as an A/B split test, right? Or kind of a similar experiment that you might run, or just kind of consider this, right? Josh wants to know if playing music during quizzes affects students' performance. He teaches 3 sections. So he plays 3 different kinds of music, right? He plays classical music in one class, light instrumental rock in another, and then no music in his 3rd class. And so then he gets the results, right? So he's comparing 3 groups and he gets the same average performance in each class. And so the question for Josh is now, did it work or did it not work? From the perspective of average comparison, so if you were to do an ANOVA analysis, for instance, you might say, no, there is no difference whatsoever, right? Or a t-test, and you will do a t-test only if there are 2 groups, ANOVA if there's 3 groups or more. And so you're like, okay, no difference, it doesn't matter, I can play music or not play music, who cares? But again, if we dig deeper into the distribution, we have to consider the spread of the distribution. And so identical mean scores do not always indicate identical distributions. And if you were a student, for instance, you might want to be in a different class depending on what the underlying distribution is for a particular grade, for instance. And the reason why this is so important, because this ties directly into our understanding of probability and our ability to make kind of solid probabilistic decisions, whether it's risk assessment, right, or again, making choices where to invest money and, so on and so forth. So the spread of the data is very important to take into consideration. You want to consider your goals, right? So assuming that 5 or higher is a passing score, if your goal is just to pass the class, you do want to be in class A. That's 100% guaranteed passing score. Who cares that everybody got a 5 out of 10? Everybody passed. The further you go down on the right, the more spread you have in the data, the less are your chances of passing, right? So here we have some people who didn't pass. Here we have more people who didn't pass. But if my goal is to get the highest score possible, let's say I want to go to a prestigious graduate school or land a very high-paying job where grades matter, right? Get a stellar letter of recommendation. I want to be in this class where I at least have an opportunity to earn a 9. Like I want to be that one student that earned a 9. And that is not possible in class A, right? Similarly, when we look at salary distributions, right? When you look at the profession or occupation where those very high incomes exist and you want to go for it, right? You don't choose to be a teacher if you want to have a chance of making $5-10 million a year, because those salaries pretty much non-existent in that profession. You want to be a lawyer, right? You want to be a doctor. You want to be a data scientist potentially, right? And so again, the spread matters. From the perspective of data evaluation, if the scores are very spread out, however, each individual score provides a poor representation of the entire distribution. So again, the more spread out the scores are, the less information you get from individual scores, including the average, right? So if the scores are very spread out, the fact that the average is 5 in the last group might not mean as much to me as in groups A and B, where the scores are much more clustered together, and that average is a much better representation of the data as a whole. So to kind of conclude, and I hope I didn't go too fast through too much information, descriptive statistics play a vital role in our ability to accurately draw conclusions from data. You do want to do them whenever you encounter a new data set. That should be like your first kind of exploratory dive as you're cleaning and making sense of what's in front of you. When analyzing data, you want to make sure that you explore the key statistics for the variables or combinations of variables. And please do not skip the graphs. Those graphs are enormously important in helping you understand what is happening with the data, what are some potential quirks, or like what looks unusual, and things like that. And when consuming database information, you also want to look for missing details. Were you informed that the distribution was skewed? Were you told about how the data was manipulated in any way, right? You want to use your knowledge of descriptive statistics to ask those critical questions and demand to see the graph. If you're in position to demand to see the graph, right? If you're in some kind of presentation, somebody's giving a presentation to you and you say, hey, can you please send me a copy of these data, but include the graph, like what the distribution looks like? I always suggest to do that, because you will always get more information out of comparing, let's say, numerical data like central tendency to a graph. You'll get a much clearer representation of the data. This is it for me today. Thank you so much for being here and for watching. And let me know if you have any questions. And I hope you found this informative.
Yeah, thank you. Thank you. It was very good.
Yeah, thank you. Definitely.
Fantastic presentation.
Yeah.
Thank
I'll,
you.
I'll stop the recording.